Hello, this is Saturday, the 5th of December, but I'm making this for the 4th of December for Friday. So it's Saturday morning. So go ahead and share the screen. Here we go. This is for class 26, Pkt2. Last night's to-do list, and I think I'll start the class. If there's homework to be looked at, I'll start the class like this. Last night was to work on 212, 5, 6, 11, and that's for the dolphin check. Go around the room checking dolphins. Now, we're going to do 12 in class, and this is for 2, 12, 5, 6, 11. So we're going to do number 12 today, and that'll finish 212. So for in-class kids, like I say, I'm going around giving dolphin stamps. For virtual kids, the way they get their, quote, dolphin stamps, so the points for those dolphin stamps is when that sheet is done, they submit. That's going to be bad. I think we'll do a submit. Yeah, I think we'll do a submit, but on the assignment, I'll put virtual students on it. And that'll be, so you'll have to turn in or submit 212 by a certain time, maybe Sunday, maybe Monday, but it's just that's the only we can do it, I think, fairly. Okay, because it is worth 20 points, these dolphin stamps. When you put them all together, 2 points each, 10 stamps. And I think if you'd done all the work on 212, you would have gotten 10 dolphin stamps, or close to. Okay, so today we're going to work on 11. Now so we talked about in class, we worked on, I went around and checked 5 and 6. Then we worked on 11 together. So let's work on 11 a little bit. And we discussed asteroids. Let me turn my camera back on. So what we talked about asteroids is that what's going to wipe out species is not the coronavirus, not wars, not even nuclear wars. It's going to be an asteroid. So there's always, like for viruses, there's always people that are immune. But for an asteroid, there's no hope. So a big one. The dinosaurs, I'd always read that it took up to 1,000 years for dinosaurs to finally die off after the impact. And they found that crater at Chicxulub, which is off the coast of Yucatan. Geophysics. But then the latest on that I heard last year was that it came down, sent a molten plume up into the atmosphere that rained down fire on the Earth, and the dinosaurs were probably mostly gone within 2.5 to 3 hours. So what survived, right? The shrew, right? Which kind of led to us eventually. But that's the kind of thing that wipes out entire species. So impacts, like, and I need to get this out and show you guys in class, but I have a poster that shows all the impacts on Earth and what it wiped out. And you can see it, sometimes they wiped out 90, 95% of the species. So all of that said, we will get hit by another asteroid. I mean, it's just going to happen. It's not like it's active. Our solar system early on was very active, and we got lots of asteroids hitting the Earth. In fact, that's where the moon came from, right? A huge impact. There was a planet called Orpheus and that orbited in the Goldilocks zone like the Earth does, it probably would have had life on it as well. I think there's some theory that if we did not have the moon, we would not have had tides, and therefore we might not have had life on land anyway. So there is the impact of the moon on evolution, but so we didn't really have a moon, and then Orpheus and the Earth collided like 4 billion years ago or more, and that formed actually a ring around the Earth. The Earth had a ring around like Saturn. This isn't just me looking on Facebook or something. These are studies that have been done. There's TED Talks on this. So we had a ring, and then it coalesced into 2 moons. We had 2 moons for a while, and they finally came together as 1 moon. We're an unusual planet to have a moon this big, and 1 moon this big. But that plays a big role in evolution. So because this fall is talking about asteroids, I took the time. So we do have an asteroid coming at us called Apophis, and it's not like it's coming from way out and beyond our solar system and finally coming in. Well, it's not even like Halley's Comet, which goes way out to the Kuiper Belt and finally comes back in. The Apophis is orbiting the sun in the same distance away as we are. It's at a different plane, but we cross paths with it every once in a while. And Orpheus is huge, and I was saying in class it was like massive, like Texas size. I don't know if it's that big, but it's big. You can look it up on Wikipedia. Apophis. Orpheus was the earlier planet, but Apophis is on a collision course with us in 2029. Now, it's not going to hit us. No one says it's going to hit us in 2029, but it's going to come close. I don't know if it's a bullet burn. A bullet burn is when a asteroid or a rock comes between the Earth and the Moon. That's a bullet burn. But I don't know if it'll come back close, but if it hits the keyhole, there's something called a keyhole, a gravitational keyhole. And if it hits that keyhole in 2029, when it comes back around in 2036, 35, somewhere in there, 2030, 2036, somewhere in there, it will hit us. And at that point, there's not much. At that point, there's not a whole lot we can do about it. Now, the odds of this happening are still minuscule, like less than 1%. So don't worry about it. Nothing to sit up. You got enough to worry about. But I just find it interesting that we aren't really doing a whole lot to prepare for asteroid research. And considering that's the one thing that's going to kill us or wipe us out, we're spending all this effort trying to avoid, getting COVID. We're all wearing masks, and there's like 1% chance, right, that you're going to get sick and in the hospital. It depends on your age and all, but we're taking all these precautions, but we take no precautions hardly when it comes to asteroids. I mean, Obama did push for at least some asteroid research. A lot of it got cut back, but we need to be putting a lot of money into it. I think just Americans and the world in general just doesn't think about it. If it's out of sight, out of mind, and if there's not one coming right at us, like next week, and by that time it's way too late. So you have to be, and you can't like send up a ragtag team of oil well drillers and they drill a hole and put a bomb in or something. That's not going to work. These things are too big. So if you know 30 years in advance, you can send up probes, attach sails to solar sails, and you can make it, if you can make that asteroid move like 1 degree or a half a degree over time, and then that would make it avoid Earth. So you got to know your Newton's laws pretty well to make sure you don't end up putting a sail on it, and that's what causes it to hit the Earth. But think about Apophis. Apophis, in 2029, I want to see that thing go by. I don't know if you can see it with the naked eye, but it's pretty big. So it'll just be a while to see that thing, and that could be our destruction. It won't be in 2029, but and then know that it's going to come back around closer. Will be, and then if we find out the calculations, we'll know by then. The calculations show that it's going to hit the Earth. I mean, at that point, there's not much you can do about it. It's going to be, talk about 2020 being a bad year. 2029, 2030 will be a bad year. But that point is, it's not going to happen. I find it all interesting to speculate on it, but when it comes down to it, you know, I can't just say asteroids are not going to hit, because they are. That's definitely going to happen. But whether it's as early as 36 or 2029, or maybe it's 2300, we'll get hit by a major asteroid in the next 1,000 years, most likely. Big. Okay, so now we're on number 11. I'll go back to sharing. I mean, like I say, if I talk about it in class, I want to talk about it here. This is supposed to be a catch-all, like the end of the day, kind of here's all the things we talked about. All right, so number 11 was homework, and I hope you gave it a shot, but let's go ahead. We worked it together in class. Let's go ahead and work it. Okay, we'll use purple here. So asteroid traveling at 23,000 miles per hour, passes Mars. When it begins to accelerate towards the sun at a very small number here, 0.005, that's 0.005 meters per second squared. Well, the acceleration due to gravity is about 10. It's 9.81, but it's about 10. So we're looking really, hardly noticeable acceleration, but over time, 24/7, that starts to really increase the speed. Remember, acceleration, if acceleration is constant, and it's not really constant, but we're going to give it average acceleration, then position change is parabolic. So it's so even though it's a low slope on the velocity increase, that translates to a exponential or parabolic rise in distance. All right, so the Earth that's my delta X, distance away from Mars, and that's not a solid number. That's just at that particular point. Okay, because we vary obviously with the rotations. We vary how far we are from Mars. How fast will the asteroid? So we're trying to end up with, looks like how fast. So we're looking for miles per hour. So we're looking for V final. So pretty obviously here, since this sheet is based on the third orange equation, this is the third orange problem. So we have V final squared equals V naught squared plus 2a delta X. And lucky for us, it's already isolated. So let's just go ahead and solve for it then. V naught then is V final, and is the square root of everything. It's going to be a lot under there. So I told the students you can write a little note on there, say on paper. You can do the same thing on 12, put on paper, in notes. And then you can answer, you get plenty of room. I didn't give you a lot of room here. You have plenty of room there to answer it. And the doubling effect is you get to add to your notes and your note score, and that'll help. Remember, notes are 100 points. So V naught squared. Now, I can either put this in terms of, what do I want to do? I want to end up in miles per hour, so I'm going to leave it in miles per hour. So I'll leave V naught in miles per hour. So we have 23,000. I'm not going to write some of these scientific notation unless this is a really big number. Miles per hour squared plus. Now I will need to do some conversions. If this is miles per hour here, this is miles per hour. When I end up in miles per hour, this whole thing this whole part has got to end up in miles per hour. You can't add apples and oranges, right? You can't add miles per hour to feet per second. I hope you see why. You can't do that. So I'm gonna do some conversions here. So 2, and then the acceleration, just write them down as they are. That's the good thing about this. Acceleration is, I won't put in scientific notation, 0.005 meters per second squared. Oops, that's illegal. I'm gonna wake up here this Saturday morning. Meters per second. I'll go and put second dot second. I mean, it's second squared, but it's a good idea always to do that, just so you can kill them off one at a time if you have to. It can't hurt to do it that way. And then my delta x is, now this is such a big number, I'm going to leave it in scientific notation, 5.6 times 10 to the 7th kilometers. And that's just over 1. Okay, I'll put the squiggly line in saying that I'm done. It signifies that I'm done with all my givens. And now the rest is all going to be conversions. And I'm trying to end up in miles. Actually, I'm trying to end up in miles squared over hours squared, right? So I'm taking the square root. So my ultimate answer over here needs to be miles. It needs to be miles, put it way over here. I'll give myself plenty of room. My ultimate answer needs to be miles per hour, something miles per hour. So underneath the radical, because I'm going to take the square root, underneath the radical, it has to be miles squared over hours squared. See that? So double slash, when I end up under the radical, I'll have miles squared over hours squared. Okay, so now let's get to work here. I gave you some conversions I see up there. If I give you conversions, you're probably going to need to use those. Well, not say probably, you will need to use those on a test. So might as well just go with that. Okay, I see a meter there. So I'm going to go attack that meter real quick. 0.305 meters in a foot. I like to bring out the green kill pin as soon as I can. So my meters go away. It didn't really help. I mean, I switched from meters to feet, I guess. I still have kilometers to deal with. So I can tell right now I'm going to need probably feet squared and then a feet squared and a mile squared. So I'm going to go ahead and get that kilometers and the meters. Actually, well, it doesn't matter. Okay, so kilometers, and that's 1,000 meters. Slash, and kind of keep track of where I'm at. So now I have still got those meters back on top, but let's get that. I know it seems dumb, but I'm going to go ahead and do it again. I'll put feet up here over 0.305 meters. Let's kill that off again. Meters and meters. And then now I have feet squared. So I circle when I'm going to keep it. I slash it if I'm going to kill it. I circle if I'm going to keep it. So I have feet squared on top. So if it's feet squared on top, I can kill it and turn it to miles squared. And so I say, okay, there is in a mile squared, there's 5,280 squared feet squared. Gotta make sure you square the number as well. So what am I doing? I'm not saving feet. I'm sorry, it's my bad. Feet die. The feet squared die. The feet die. Sorry, feet. Miles squared is what I'm saving. Sorry. I know you're yelling at your computer screen. Okay, I really need to wake up. I'm gonna drink some espresso this morning. Okay, too late. So once the Zoom starts, you can't stop it. I mean, you can pause the recording, but you can't stop the Zoom. Now we need hours squared. It looks like that's going to be easy because I see back over here I have seconds squared back here. So let's just go ahead and go 3,600 seconds in an hour, but I'm squaring it seconds squared. over hours squared. Now I'll bring out the drink kill those two, and the second squared goes away. I'm hanging on to the hour squared, and it looks like I have miles squared over hour squared, which is what I want. And so now it's just a matter of punching in your numbers. And if it was a test, seriously, folks, if that's a test, I would stop right there and move on to the next problem. Students don't finish tests. Mostly the reason I've noticed when I'm grading tests is they'll be humming along, and then they'll get to a problem that they can't solve, or they can't. I usually give answers on tests because, just to kind of make you feel better, right? That you did it right. That backfired on me because students would get the wrong answer and they would not leave that problem alone. And so they weren't finishing tests because they knew they were wrong, and they kept just at one problem. Then the bell rings and they go, "Hey, do I have more time?" I said, "No, you don't have more time. You don't get more time in college. I'm sorry. Unless you're on IEP or something, you don't get more time." So you've got to do a little triage. I'm trying to get your brain, ready for college. Physics classes in college give you 21 questions, at least when I was doing engineering physics, and you had like an hour. No one could finish. So your job was to just gather as many points as possible with partial credit. Never, ever, ever leave anything blank. So in this case, it's okay. I mean, the actual answer, this is a test question, it's worth 20 points. At this point, you got 19 out of 20. Well, yeah, I mean, you do. You have 19 out of 20. Because I see you've done all the work, and you only get 1 point for all that punching into a calculator. And you can agree with me that you probably got a 50-50 chance of making a mistake, and then you wouldn't get the point anyway. So if you had this, I promise you would get a 19 out of 20. Okay. And because I'm kind of lazy and I spent too much time on this problem here, the answer, it says, is on 11, 57,600 miles an hour. And so that makes sense, 57,600 miles an hour. So remember, it was going, when it was around Mars, it was going at 2,300 miles an hour. So it was a little more than doubled. Even with that very small acceleration, it's still more than doubled in speed. Okay? All right. And then you could go back now. Now you could go back, and now that you know all that, you could solve for T. A part B on this question might be, how long do we have before this hits us? Now, this was assuming that it's on a straight and narrow path. Of course, it's not. There's all kinds of gravities involved, being slingshot around Mars. It's going to kind of curve into Earth. There's the whole sun involved. So I know, I realize I'm taking, but that's what you have to do early on in physics, is you have to take these complicated situations and simplify them. Like you say, okay, this rabbit is a dot. This car is a dot. So even though we know there's all kinds of physics involved, we're slowly getting a little more complicated as we go. Remember early on, we couldn't even talk about things that were accelerated. Now, next week, starting Monday, we're going to start talking about more about vectors, in addition to vectors, head and tail, and components. And we'll spend probably a good chunk of the week on that. We've got to finish. That's 214. We're still going to do 215, 216. So I got a lot to do in the next 7 days of school because, well, really, I guess I have Wednesday still, but the week after. But I have 8 days, I guess, before finals. No, because that's a test. So I have 7 days to get through those 3 worksheets plus a bunch of stuff on vectors. All right. Well, that was fun. Now let's do 12. And 12 is the hardest problem. I think 11 is close runner-up, but 12 is the hardest problem on this sheet. And you'll see why in a minute. Okay, so we have Crazy Joe. Crazy Joe is I showed the kids a picture of him. But think of the wildest, craziest guy you knew. Everybody has some wild uncle. and that's Crazy Joe. My brother and I worked a lot of construction. We worked for a company called Brown and Root, which built the coal processing plant north of Stillwater. We worked as built with Conoco and other companies on oil lines, and I was a garbage man. He was a garbage man with like 2 summers. So we always worked together in the summer. He's an older brother of mine, but it was fun. But we ran into the craziest. I mean, the crazy one summer. Well, actually, I only had this job, worked in a canning factory, and there was some nuts. That company was called Owens, Illinois. Anyway, so Crazy Joe, he's an amalgam of all these crazy characters that I've known. You need to go out there. You need to go out there and work, because that's where you stay in school. School's wonderful, but you got to get out there and work, because that's where you meet all the real people. Summer, maybe work every summer if you can. You can go to summer school in college, but you got to get out, get away from that school. Go work, go work construction somewhere. I learned so much. Electrician's helper, learned a lot about electricity, woodworking, worked in a lumber yard for a summer. That was really cool. Okay. At that point, I ran a forklift. I drove diesel trucks in between Ponca City and Blackwell, Newkirk. Anyway, so good times. So here we are, Crazy Joe. He's in a souped up 68 Camaro. He's going at 80 miles, and that's unfortunate. The units got marked off 80 miles per hour. Go back to purple. 80 miles per hour, and that's going to be his V0. And he does it. The question is how many seconds, so we're trying to find time, solving for T. So I said this sheet, I guess I'm wrong. I'm thinking of 211. 211 is all third orange. This sheet is both first, second, and third orange. Anyway, so we're supposed to find, this case looks like probably second or first orange because we're trying to find time. Well, it'll take Joe to get to the state border 500 feet away. So that's my delta X. If he maintains a constant acceleration of 8 feet per second. There's my A. Okay, so looking at what I have, I'm trying to figure, it's going to have to be, it looks like the second orange. So my equation will be, and then you could do, it didn't say to do a drawing, but a drawing is always good. Probably should say, on a test it would. So you could put all these in a drawing. But anyway, so I didn't have much room. So the equation is delta X then equals V0 T plus 1/2 AT squared. Now, I've got to solve for time, and I'm going to hit, well, you should hit pause, and then you try and solve for time. Let's see what happens. And pause. Okay, so you're back from pause now, and you tried it, and I think you found out there's a problem. Now, the only way, you cannot isolate that T. The only way you can isolate the T, but it ain't easy. The only way to do it is to employ the quadratic formula. So let's go back to algebra 2 for a minute. And the quadratic formula, let me change to black here, is if we have a polynomial in the general form, and so this is a general form. And the general form of a second order polynomial is ax squared plus bx plus c equals 0. Okay, so in order to solve for x, you have to say x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so that's the quadratic formula, and we use it a lot in physics, turns out. So what we have to do is turn this into what's called the orange quad. So I'm going to put my equation, my second orange equation, into the general form. So the general form of the second orange equation is 1/2 a t squared plus v naught t plus the opposite of delta x equals 0. Okay. So now this is my A, capital A. This is my B, and this whole thing is my C. So I can just now plug it into, you know, that's what I'm saying. Go to you should probably just be on a piece of paper now in your notes. Let me erase all this while I'm this is going to take me some room here. You can't do this though. So you should be in your notes. Okay. Let's go then go back to purple. And let's plug and chug. Okay, so into the quadratic formula, when I plug and chug that in, I get, oops, all right, thought I got rid of all that. Okay, when I plug all that in, I'm going to get t now, solving for t. T, come on, man. Here we go. T equals the opposite of b, which is the opposite of v naught, plus or minus the square root of b squared, v naught squared, minus 4ac. Well, that's 4 times 1/2 a times negative delta x all over 2a, so all over 2 times 1/2 a. So this, then to simplify this turns into t equals the opposite of v naught plus or minus the square root of v naught squared. Now, it's minus 4 times 1/2, it's minus 2a, but it's minus a minus, so it's plus 2a delta x, and a is an acceleration this time, little a, all over a, okay, not quite as melodic as the quadratic formula song. All right, so that is the quadratic formula, and we call it the orange quad. This works for these kind of particular problems. Now there'll be a blue quad for free fall. In class I post this, I hang this in the ceiling. So for virtual kids, you're just going to have to write this down, and it'll be on the next equation sheet, but you're going to have to write it down somewhere so you have it handy. All right, well, the good thing about that is this problem, which I said was the hardest problem on the sheet, mainly because of that. Now that we've done that, it's just a matter of plug and chug into the orange quad. So to find our time, but we do have a little bit of a unit issue, I see. We're trying to end up in seconds. So I think I want to convert everything into feet per second and not miles per hour. On the asteroid problem, it made sense to put everything in terms of miles per hour because of what they wanted the answer in. But here, it makes sense to put things in terms of feet per second. And by the way, Crazy Joe is an American. He's American and freedom-loving. And he does not ever do problems in metrics because metrics come from France. So Crazy Joe, all Crazy Joe problems are in English, or what we call now imperial units. Okay, so let's get this V naught in terms of feet per second. So a little quick analysis inside the problem. And it's a short one. That's 80 miles per hour over 5280 feet in a mile times an hour over 3,600 seconds. I think that gives you 117. And then minus, okay, then plus or minus that, then plus or minus V naught squared, which I'm telling you, when you do the math there, you'll find it's 117. So 117 feet per second squared plus 2 times acceleration, which is in the right unit, 8 feet per second squared times delta x, which is in the right units, 500. I can't, my eyes, man, I can't. Yeah, 500 feet. Then that whole thing is divided by acceleration, which was at 8 feet per second squared. So notice that you're going to have feet per second up here. You'll end up in feet per second here because the green kill pin will wipe out the hours and the miles. And you're left with feet per second here. And then on this, underneath the radical, and remember this is called the determinant. So underneath the radical, you're going to end up with feet squared over second squared. But then square root gets a feet per second. So apples plus apples. And then below it, you got feet per second squared. Well, the feet cancel. One of the seconds comes up top, and so it ends up being in seconds. So it works. So once again, on this problem, this is the point where you probably say, okay, I'm going to move on. And because even if I see the right answer, I'm still going to go back and check your work. It's hard in physics to cheat because you can't just get answers from people. You got to go back. You'd have to get the entire test. And I have had students in the past that try to take pictures of it, and they've gotten caught. Every time they've gotten caught, and that's like academic suspension. So it's a pretty bad thing if that happens. If that ever happens, I catch that. That's like an automatic F on the test, and then sometimes you have to leave the course. So that's pretty serious business if you're doing that kind of cheating. Most cheating is out of desperation, right? Your eyes start wandering. That's why we have privacy fences to kind of make so in class. Now with virtual, I just have to trust you guys. Okay, so anyway, the T ends up being, so the point is that I'm always going to check your work. So just put in, and then if you, here's the worst thing you can possibly do. Put the right answer and have the wrong work. Then you're in real trouble. Because then I know something ain't up. It's just really hard to, you got to outfox me on that. I've been doing this 35 years, so it's hard to do. Not that anybody would. The T here ends up being what? 3.8 seconds, if I remember, 3.8 seconds. And you can do the work and prove that to yourself. But once again, if it's worth 20 points, I would stop right there. I would stop before I even did the calculator stuff, and I would just say, okay, just leave it. Just walk on to the next problem. Then if you have time at the end, come back and do it. But save all these complicated calculations for later. Okay. Now part B, okay, let's go to the next page. There's that. You'll have that somewhere. I'll put this in a screenshot. But part B, here's my work from last year. Part B is to find the final velocity, and that's pretty simple. Once you have acceleration, you have time, you have V naught, you can just plug and chug. And they get about 148 feet per second, and it's approximately for like feet per second. To go from miles per hour to feet per second, you multiply by about 1.5. Okay, so miles per hour is always about 2/3 of what feet per second are. So I automatically know that 148 feet per second is about it's about 100 miles an hour. So he's going from 80 to 100 in 3.8 seconds. That seems certainly reasonable. Okay, you always want to make sure it doesn't seem reasonable. Okay, so did that. Then the last thing, now Miss Millington, she was kind enough to let me take a picture of her sheet. She has very good handwriting last year, very good handwriting, and so I took a picture of it, and that's going to be my key, because this sheet is like a Frankenstein of old sheets. So I didn't really have a key ready to go last year, so I thought, well, she writes better than I do anyway. So now I realize I made it too small for you to see, but I will post this key. It might not be till early next week, because I want to get the virtual kids. I don't want virtual kids just to copy down the key. Not that you would, but sometimes desperation takes place. So I want the virtual kids to turn in their, like the kids had to do in class, right? They're going for dolphins. They don't get to look at the key. So virtual kids shouldn't either. So I'll probably make that due Monday night for virtual kids, this sheet to turn to submit. So make sure I do that. Submit this for Monday night, virtual kids only. And then I'll post the key, probably Tuesday. Okay. Now, the other thing we did in class was this, but yesterday, Thursday's Zoom, we did this on. So in fact, we just really talked about it, but I think that might about do it. What else we got? Okay, I do want to talk about this, because in most classes, we start at number 6. And I was going to try and get through 6 today too, but after all the working 11 from the homework, and then doing 12, and then working on the girl in the Jeep, and then we had Flashback Friday, we kind of ran out of time, and I really didn't want them to have to, that's a lot. I was asking a lot for them on Friday, and they were really doing great in class. They're just they're great kids, and so they were trying, and so I don't want to push them too hard on Friday. So we didn't really do much on this. We did some stuff on this on Thursday. So let's at least for virtual, let's at least set up number 6. It's in class work. I think I might make it homework Monday, but let's at least set it up. Okay, so let's say you're an engineer and you are to design a runway that will accommodate jets. Say you're working for Richard Branson, and he has an island or two, right? Let's say he wants to build an airstrip on his island, and he wants to land fairly big jets there, like he wants to be a fuel station or something. So the question is, if you want, this is kind of what engineers do, right? They're given parameters, and then they got to say, well, how long does that runway have to be? I think that's what we're looking at here. So an engineer to design a runway to accommodate airplanes that must gain a ground speed of 140 knots. Okay, 140 knots. Before we'll get to that, what the heck's a knot, right? We'll talk about that in a second. Okay, 140 knots. Before they can take off, the planes are capable of being accelerated uniformly at a rate of 175 kilometers per hour per minute. Okay, I like that. And then it gives some conversions there. 1 knot is 1.15 miles per hour. And let me turn this off for a second. Stop sharing. All right, so I want to talk about knots for a minute, the history of it. It's really a fascinating history. If you're a sailor, you know what a knot is. If you're a pilot or trained to be a pilot, you know what a knot is. So on boats and on planes, they still use knots as a speed historically. So don't quote me on this, but we're looking 1400, 1500, 1600 certainly, when they had big ships like schooners and stuff. When they had the big ships, early on, ships would wooden ships would not leave sight of land. You have a crow's nest. Make sure you can kind of keep an eye on that land so they knew where they were. They looked for landmarks, lighthouses, whatever. Well, they didn't have lighthouses back then. But maybe they did. Maybe they had something. They didn't have obviously didn't have an electric light. Maybe they had a big, I don't know what they did on points. There's a good question. What did they do before they had lighthouses to let the sailors know where the rocky point is? Fire? I don't know. So anyway, so they would not leave land because once they lost sight of land, they were lost. Now they developed something called a sextant, and with a sextant, like an astronomical instrument, and you should look it up, it's pretty cool. But in fact, sailors today still use sextants. But you can map the stars, and from there you can know what latitude you're on. You know how far, you guys learned, these kids in class knew what latitude and longitude was. So they know what latitude they're on, how far above the equator, right? But they didn't know what longitude they were on. Remember, longitude runs north-south. There's no way, with the Earth spin and all, there's no way that you can determine the longitude. You can't look at the stars. I mean, this was a huge contest. There's a book called Longitude. And there's a really good book in my room called, and I show it to kids, called Illustrated Longitude. And it's all about a contest. They put the greatest minds to work. Even Newton kind of got into it. So it must have been around 1700s. He was looking at Jupiter and things like that to come up with a way to figure out what longitude you were. Finally, a guy named Harrison figured it out, but then he got ripped off. It's an interesting politics and science and the time. If you like historical pieces, really good. Ought to be a movie. But so one of the ways that the problem on boats are they had pendulum clocks because by that time Galileo's son and I think it was Christian Huygens that invented the pendulum clock. The thing is, pendulum clocks don't work so good, right, on ships because they're swaying back and forth. So they had hourglasses, but that's not going to give them, they had to develop a time mechanism. And really, to find longitude, it was a matter of timing. Now we have GPS, satellites, and all that, but you had to time how fast you were going, and then the captain would map it out, right, as to where they are, where the last coordinates were, where they are now. And then link that up with the latitude and give a pretty good idea in the ocean where they were. Of course, before Columbus, they didn't even know the New World was over there. I mean, the Vikings did. But anyway, so you had to figure out your velocity. Just using a red equation, you had to use, delta x equals v times t. So you had to know your velocity, and you could time it. And so what they would do was, this is what they would do. They would take a rope, the sailors would, and you tie knots in the rope, and I don't know if it was 5 feet or whatever, every 5 feet or something. And then they would tie that rope to a log, an actual log, big log, and they would throw that over the back of the boat. And then the idea was that log would bob up and down, and the boat would keep going. And so they would hold the rope, and as the ship goes on, the rope would go through their hands, right? And then every 5 feet there'd be a knot. And so they would count knots, and they would take, I guess, an hourglass or a minute glass or something, turn it over, and then they would count until that sand runs out. They would count the knots. So if you go on 10 knots, 140 knots is for planes, but for boats, 10 knots is a good speed, 20 knots. So they would count 10 knots, and then they would take the log, they'd pull it out of the water, they'd dry it off, they'd take it to the captain, and the captain, they would write right there on the log the date and the time, and based on where the sun was or whatever. Because remember, early on they didn't have clocks, they didn't have like tick-tock clocks, or like gear mechanism clocks. So he would write down what the time was, and then would write down the speed, how many knots they were going, and the direction and all that on the log itself. So that's where captain's log comes from. So the word we still use today, like, oh, you log your time, that comes from a log. And then they would take that log at the end of the journey, they would take that back to Spain or wherever they would plunk that down as there's our evidence of where we were, what we were doing every day we were gone. And I don't know, maybe some of those logs still exist. I'm talking 500 years ago. That'd be kind of cool to see some of those old logs. Someone can look that up and see if there's a log still around. So that's what a knot is. And for some crazy reason, let's go back to sharing again. For some crazy reason, we never stopped using that. I guess because, there's a whole folklore in ships. And I don't know why. Now, the planes, obviously, Wright brothers, now we're talking 1900s, early 1900s, like Kitty Hawk and all. I don't know why they decided to adapt nautical speeds, but I mean Henry Ford or whatever didn't bring in nautical speeds when it came to automobiles, thank goodness. Anywho, so a knot is about 1.15 miles per hour. Okay, so here we go. I set up the unit analysis. Looking at this, we're trying to find, we're not going to do the whole thing, we're just going to get started. How many miles long? So we're trying to find delta x. And so we know speed, we know acceleration, we're trying to find delta x. I don't see anything about time, so it looks like probably third. So we're doing v final, go for the points there. V final squared equals v naught squared plus 2a delta x. Does that sound right? We're trying to find how many miles. We're trying to solve for delta x. Yeah. We did catch a little break here because the plane's on the runway, right? So V naught is 0 when it's getting ready to go. So that makes this easier. We're trying to solve for delta x. So when I do that, delta x is going to be v final squared over 2a. I probably should go back and write all these in the gold standard format. But anyway, maybe one day. So my first block's going to be I'll put the 1/2 in there. Get my givens done. And then my v final squared is 140 knots. So write it in as it shows, 140 kn for knot squared, 140 squared knot squared over 1. Isn't that weird? I mean, miles per hour is 2 units, knots is 1 unit, and that's I just realized I wasn't sharing the screen that whole time. Okay, sorry. Let's catch up. Look at the screen here. I am really, I'm tired. I just left the link. So there's what I was doing. I apologize. So let's catch up. So 1/2 v final squared. Here's what I was talking about right now. The v final squared is 140 squared, not squared, over 1. Well, 1 squared, but 1 squared. If you want me, just for completeness sake, I'll put 1 squared. But that, like, speed normally is 2 units, right? It's miles per hour. It's feet per second. It's meters per second. But knots is 1 word, and that's one of the reasons why I'm doing this problem. That's what makes this problem hard. And then the A is flipped, and so when I flip that A, I get 1 over 175, so 175 goes on bottom. But the units, that's that weird thing about units, is kilometers per hour per minute. But remember, those hours and the minutes come up top. Okay, that's as far as I want to go on that one. I've talked to my hours limit here, so that's as far as any class got. Some classes didn't get that far. So I can't just leave this alone, let it go. We'll probably do, we'll do 6A in class on Monday, and then 6B I may send to the board, I guess. Yeah, probably send to the board on me. Okay. All right, so everything went okay, except I screwed up on it last year. All right, so I'm out of time. I will see you guys Monday for Virtual Kid, Monday at 4 o'clock. See, my neighbors are here, and they thought they moved. I don't know. I think they're having issues. They got a little kid too, a little white, cute kid. Anyway, I hope they're all right. They're good people. Anyway, oh, Mailman's here. I gotta go. Talk to you later.